Yes.
So last time or last week we did linear regression in R. Yes.
Yeah.
We fit the model. We did ANOVA to see if the model is significant or not. So there are two outputs that you can get. One is the coefficient summary. That gives you coefficients and their significance. Is a coefficient significant or not? In other words, should you keep a coefficient or not? So a coefficient summary from R is going to give us the values of the coefficient and the significance of the coefficient. What do I mean by coefficient? You have y hat beta naught hat plus beta 1 hat. X would be the fitted model. What are the coefficients? You're missing something. Hat. Beta naught hat, beta 1 hat, they are estimated. Those are the coefficients. And if both beta naught hat is significant and beta 1 hat is significant, they both are significant, then the entire fitted model is significant. Do you agree? Okay, thus you can verify again using the ANOVA summary. That is going to provide us with overall model significance. Of course, one can look at beta naught hat, beta 1 hat, significance, move on, but ANOVA summary is going to give us additional information, one of which is R squared. It's a regression. Oh, what is R squared? Correlation coefficient.
No, it's the
It is the coefficient of something. Start with. You must be determined to give this answer. That's what I did. Coefficient of determination.
Oh no, I said determinate.
That's correlation.
Of course, R squared and R directly, they are related directly. In other words, last time we had linear correlation coefficient. You square that, you are going to get this. However, today's case, when we get to multiple linear regression, it's not that straightforward. What does this tell you? The amount of variation in y that can be explained by x. In other words, how good of a job is this fitted model doing in explaining the relationship between y and x? In other words, it is a measure of model accuracy.
Just by X.
Well, let's see. Y has a name. What is Y called? What type of variable is it?
Dependent.
Dependent and X.
Independent.
Okay, what are other names for it?
Oh, like,
Tell me the same
oh,
thing.
there, now you're asking.
Start with the letter R. The independent dependent part is easy because Y depends on X, right? But there is another name for Y. Starts with the letter R. If
Regressive or regressor.
Oh,
Re-
the residual, residual
semantic,
response.
very good, response. If you read that statement, the amount of variation in the response that can be explained by X, hence. We can call X as the explanatory variable because X is going to explain what is happening in Y in terms of the variability that we see in Y. When you first did 2023, assuming that you remember stuff, broad assumption, I guess you're about to violate that model assumption right away.
Good one.
Using the fitted model, one would do something. That is the purpose of linear regression. What is that one thing that we do? Once you fit the model, we use that model to do something. Starts with the letter P.
Predict.
Predict.
Oh, good answer.
So we've got another name, which is predictor. So explanatory variable, predictor variable in the same thing. Reason being, Y is explained by X and Y can be predicted using X. So if you know that the coefficients are significant, if you know that the overall model is significant, you can make predictions. Good. Thank you. Let's see if you remember stuff from last time. Once you fit the model, you have to test for assumptions. What is one of the assumptions?
Oh, how to test or just the assumptions? Normal
Normal what, Phoebe?
data.
Okay, but what's normal answer? Is it for X, is it for Y, or is it for both X and Y? So, variability in Y is due to not this, but epsilon. And the assumption is epsilon is normal with mean zero, some variance, sigma squared. Yes? Epsilon is this arbitrary noise that gets added, correct? Is it possible for us to accurately come up with that epsilon? Do you follow my question? So variability is introduced in Y in an arbitrary manner, is it possible to get an accurate value of that epsilon? We are dealing with random stuff. Sydney, you know the answer. Is it possible? No, we can't get that exact value, so we estimate it. So the estimator for epsilon is just epsilon I hat, that has a thing.
Residual.
Very good. You have the actual value yi that is in the data. You use the model to fit the relationship between y and x. You're using the fitted model to get that fitted value. The difference between the two will give you a residual. We can use the residuals to see if we violated assumptions or not. How? I believe that's where I ended. I mean, we want it to be normal, so what are the rates? How can you verify normality? We can use a test, Shapiro, or what else?
We can do the QQ for
A QQ plot, okay. Something you need to linear regression.
The Beans test?
Beans test, no.
Or an
Riley,
a residual plot?
very good, a residual plot. And when you do a residual plot, what should that picture look like?
straight line.
You cannot see patterns in it. Now, for a case where you have y and x, it is not a big deal. I can determine whether the model violated assumptions or not easily. It gets harder when you get to multiple linear regression. Good? Okay, that's it. Can I erase this?
Yeah.
Okay, before I do, this, that, I'm simply going to extend it to multiple linear regression. Good. I'm not going to write it again, but I'll show it using R. The generalized linear model, it is not just meant for multiple linear regression or linear regression. There are other cases. We're not going to do all that. We'll stick to the simplest case, but I'm going to use GLM in R. I can also use L. I'll just use L. Again, that general part, it is used for other reasons, way beyond the scope of this class. So a linear model LM function in R will do multiple linear regression. Okay, what is multiple linear regression? Instead of having just beta naught, beta 1, x1, one predictor, you can have any number of predictors. Good. It is simply an extension of that simple case. Or I could say a linear model is a simple version of, a simple linear regression is a simple case of multiple linear regression. Good. You have more than one predictor. In practice, which is more realistic, this you cannot explain a process Y simply using one variable X. There are multiple things that go into play. But in terms of assumptions, same assumptions hold. I have some noise that gets added, and that noise I want it to be normal, but some variance signals point. Good. Yes. Our objective now is to, for instance, come up with estimates for beta naught, beta 1, beta 2, if you have more than one predictor. Once you go past two of them, things get hard. Why? Do you have a question?
Yeah, I was gonna say, should that be y sub I, since we added the epsilon on it?
Uh-oh.
Whoa. Oh, God.
Sorry, man.
Ooh, already suck.
I know. Shit happens.
I hate writing it.
And observations for each of the predictors. Moving on to that question, why do you think that things are going to get harder when we have more than one predictor?
More variability.
Okay. I mean, variability is because of this.
Mathematically, it'll just be a lot harder, because when you want to minimize the residual, you have to take a bunch of partial derivatives.
Okay, getting somewhere mathematically it's harder, but even before you get to that part, if y is a function of x, how many dimensions are you looking at? Take x and y. If I have add x1 next to x3, x4, what is happening to the dimensions?
Think about
It's getting bigger, and one's dimensions get really large. Is it possible to visualize them as functions easily? No. What do we do in math?
Use MATLAB.
Use MATLAB. Kind of is, but what does MATLAB use?
a matrix.
A matrix. So once you get past 2 dimensions, it is all matrices, and you cannot do well in statistics or data analysis if you don't understand matrices. Period. Good. Okay. So the goal is to fit that model
You want me to prove my theorem?
and without using R.